Good afternoon and all. Today we are with the subject name that is compiler design. Previous sessions we have discussed about various topics in the compiler design. That is role of today's talk session is role of parser and context-free grammar. A brief discussion about the derivations, that is the leftmost and rightmost derivations, and how to this position of the parser in case of the analysis and this design and tax analyzer and these phases. Also here we will look into this one phases, and then the construction of this derivation trees also. Later brief discussion on context free. First, initially we are going to take a brief overview of the parser. So here we know that the compiler phases, first phase, it is consists of a that is called as lexical analyzer phase, and second one is syntax analyzer, and third one is semantic analyzer, and the fourth one is intermediate code generation, and fifth one is code optimization, sixth one is code generation. So in all these phases, the first phase, that is called as lexical analyzer. In this, you accept the source program, whatever the program that is written by the user in the form of a lines of code with the help of C, C++, or Java, or Python, like that. Several programming languages with syntaxes. The user written programming language, such as high level language, English language like statements can be written. So this is accepted by the lexical analyzer phase, and it delivers into stream of tokens. And while delivering the token, first syntax analyzer issues a command. That command known as get next token. This method, get next token method, that is sent by the syntax analyzer to the lexical analyzer. So here, whenever token is delivered to the syntax analyzer, next step, once again it reissues the same command, get next token, until all the tokens are to be completed in this process. For example, here syntax analyzer, after receiving the token, then sometimes it validates whether the token releases the corresponding requirement or not. That means verifies this whether the token is properly. That is the job of syntax. In between, any errors or occurs, that is sent to the lexical analyzer. Errors are sent to the symbol table. Similarly, syntax analyzer also communicated with the symbol table whenever a command is to be executed with the successful results. Else error reports are sent to the symbol table. So after successful completion of a token that is to be generated by this first phase of the compiler design, that is lexical analyzer, then that is to be accepted by the syntax analyzer by this tokens, and then generate a parse tree notation. Shortly we are going to see the different type of parse trees also. So here the parse tree is the which is delivered from the syntax analyzer phrases, and then that is to be verified by the semantic analyzer with the help of the semantics of the particular language. And then the remaining phases, it is to be continued. That means intermediate code generation, code optimization, and code generation. These are the phases that is to be. So in this process of the construction of this parsing, that is, it is also called as syntax analyzer. Why? Because after execution of the second phase, that is syntax analyzer phase, parse is delivered. That is called, we are doing a parsing mechanism, or it is also called as syntax analysis or syntax analyzer. These are the different names for which the description which is to be known that the syntax analyzer phase successfully delivered the parser notation. That parser obtains a string of tokens from the lexical analyzer and then verifies the structure that is generated by the tokens based on the grammar for the source language, and then it builds up the parse tree. So I have told that in between any successful results, it is sent to that syntax analyzer phase for construction of the parse tree. Else, if any errors there, it is also reporting an error. So take who is getting releases the token, lexical analyzer releases the tokens, and then that is verified by the corresponding token structure based on the grammar, and then builds up the corresponding parse tree. That is the job of the syntax analyzer. Error recovery management will do the common erroring process in between any. This is the diagram which is describes about the concept of parser. So we already know which phase that is parser. That is in between syntax analyzer and semantic analyzer. That is the output of the syntax analyzer that is generated by the second phase of the compiler, that is called as parsed. It is also called as parsing. Now come to the context-free grammar. A context-free grammar contains finite set of grammar rules. Finite set of grammar rules. Here we can represent it is a quadruple notation. First one is called as V. V stands for variables. T, which stands for terminals, and P stands for productions, and S stands for start symbol. A variable represents set of strings. Variable represents set of strings. That means here finite set of variable, that is here the variable, another name of this one is a non-terminal symbol. A non-terminal symbols are also called as variables. That means all the letters which are capital A, that is capital T, these are all non-terminals symbols which are also called as variables. And terminals, that means the remaining characters which are lowercase letters, that is a terminals which are to be considered. First one is a non-terminal, second one is a terminal, and the third one is a production. That is here the productions are which contains set of rules or productions. Which contains set of rules or productions. In this, we are going to define the productions with which consists of variables and terminals. That means a combination of variables and terminals, and it is represented by a notation such as head and for arrow mark, that is deriving symbol, followed by product, that is a body, head, body. So the head portion generally contains a set of variables, that is non-terminals only, whereas body, which is contains a combination of terminals and non-terminals. It may contains many number of terminals and non-terminals. Here contains a combination of terminals and non-terminals. And then fourth one, it is a start symbol which is to be written at the beginning of each of the production, that is set of rules which are to be determined. In this list of productions, the first and foremost production, that is start symbol, that is to be taken by this as start symbol, as that is to be defined in this grammar. So other variables represents auxiliary classes of strings that is used to help define the language of the start symbol. So we may use different notions for representing these variables, terminals, and productions and set of rules. So these classes of strings is used to help to define this particular grammar notation also. So these, according to the context-free grammar definition, a grammar is said to be a finite set of grammar rules where quadruple notation, which contains variables with p comma t comma p comma s, where we represents the variables, terminals, productions, and the a start symbol notations. So inputs. So here the production we have considered the third element, that is production in this grammar. So here generally we represent a notation such as head defines body. Head is nothing but it is a variable. That means the non-terminal that is to be written on the left hand side of this derivation symbol. Whereas the right hand side of the derivation, it contains variables and terminals. Variables and terminals. That means here it may not contain terminals. That's why it is called as G star. V union T star. That means 0 or more number of terminals and variables. 0 or more number of terminals, and let us see the example of this one. So in this example, first a grammar G is defined. In this grammar, the first, that is start symbol, and input, that is supplied A comma B, productions, and the start symbol. So here, what are the variables? Yes, S is the variable. What is the terminal? A comma B. What are the productions? P defines, these are the productions. And what is the S? What start symbol? What is the definite? The start symbol. That can also be written as S derives. So here in this case, we are going to write the G equal to V comma T comma P comma S. So here what is variable? So this variable represents the non-terminals which are defined in this production. So what is the grammar that is defined here? Capital S. And what is the terminal? It is defined small a and small b. So that is to be written as one set. And the productions means S derives ASA and S derives BSB, S derives epsilon. That is the productions. This P. And then what is the start symbol for this productions here? S derives. So that is the start symbol. So this way we are going to write a given. So in the second example, we are going to see that grammar with a set of rules such that the first variables which appear in this one is capital S and then capital F. So this is the two comes under variables. And terminals 0 comma 1 terminals, and the productions which are supplied here, that is S derives 00S 11F, and start symbol, this is the start symbol to be supplied for this graph. So this is as simple as this. We are going to determine that the consists of variables, terminals, and then list of productions, start symbol, fourth one. So only 4 elements. These 4 elements define the grammar notation. So here while deriving this one, we are going to apply set of rules, and then we implement this quadruple set notation. Sometimes by applying this productions rules, we may derive certain set of strings also. So that derivation of the strings from the given production of the grammar may apply differently. That is called as one-step derivation or direct derivation. That means to reach the derivation, to apply this one-step derivation or direct derivation, if v is derived from u, v is derived from u, then we can write u arrow derivation symbol followed by v. Then u is equal to x alpha z and v equal to x beta z if alpha derives beta in p. Here p stands for the production. Let us see that this example through this definition through example. So here x alpha z derives x beta z or x alpha z, which is going to yield x beta z. Here the production is given A derives small a, capital A. In this example, first production is this one and second production is A derives B. Third production is B derives small b, capital B, and fourth production is B derives epsilon. So if you, for derivation of Atlas string, let us start with the first two derivation, that is A derives small a, capital A. But we are going to derive a string by applying a grammar symbol, that is grammar production, that is the set of rule capital A. What capital A contains, I can apply either this one or this one. So in order to substitute the capital A, that is small a, capital A, small a, there we are getting this results. Once again, this capital A may be substituted either this one, capital A. So here this time we have applied capital B. Capital B we can apply, and then after that the capital B may contains either small b, capital B or epsilon, two cases. Out of these two productions I can apply the capital B. Once again capital B replace, so that is to be derived one time. So this is called as derivation steps. This is called as derivation steps. So until we get the reaching the derivation string, we are going to apply. Let us see the derivation types. In this process of derivation, we may apply star indicating that 0 or more. Star indicate that 0 or more derivation steps. 0 or more derivation steps means how many, sometimes we may get the derivation step within one step, that is called a single step. If we apply several times k step or 0 or more steps, we can apply star. So here this process of derivation, say we have taken an example, and then we are going to derive a string finally. So capital A either may be received with this one or this one. So we are getting once again substituted with capital A, small a, capital A, and then once again small a, capital A. Then we can reply either B, capital B, this one. So capital B, and then capital B derives small b, capital B, once again small b, capital B, and then B derives epsilon. Here B derives epsilon, we are getting 3s, B, 2b's, and so this is the string that is to be derived. That is the string that is to be derived from the given set of rules, given productions. So these strings are derived, that is, say it is a U1, it is due to the number of steps that is to be used to derive a particular string, the process of derivation, that is called as nth derivation or k derivation steps. So repeatedly apply a process of, to obtain the resultant string, to obtain that resultant string. Parse tree, we can generate a parse tree based on the resultant production, that is derivations. So the sequence of substitutions which is used to obtain a string by this constant free grammar is called as derivation, and it is represented by a tree notation. That means previous steps which we have used are derivations, that is per u1, e2, e3 like that. So in this process of this we are going to apply a tree notation step. So this, after getting one result, so a derives small a capital A, this one. Once again capital A derives the same thing. So we applied like that. Then capital A derives small b capital B. We applied. Once again, small capital B derives capital B. Uh, capital B derives small b capital B. And then capital B derives epsilon. So we applied this step how many times? And this is first time we applied, we are getting one tree, and then once again this A is replaced with second time, and then third time. After third time we are going to replace A, substitute that derivation rule A with B. That is in the previous slide, A with capital B. So A with capital B, so that is to be used, the second derivation. So that is A with capital B, and then B derives, that is, this is the first, this is second, and then third we applied B derives small b capital B. Once again it is applied two times, and then finally fourth one we applied B derives epsilon. So here the first node is called as root node, is called as start node, that is called as root node. Root node or start of the label. So it is a tree. A parse tree is a tree that is graphically represented with the information that is available based on the derivation strings from the context free grammar. The context free grammar we applied based on the terminals, non-terminals, with the help of deriving the string, some of the steps to be used. So that is to be used, the same can be used for the purpose of generating this parse tree. Then this tree is called as parse tree or derivation tree. So it is also called as derivation tree. Why? Because we are going to repeatedly apply several derivations to obtain the resultant string. Here inside the interior node we are going to apply a variable notation, and the parent child, it is a derivation step, and leaf node, that is all the nodes which are available at the last, that is leaf nodes, that is at epsilon, and leaves of parse tree when read left to right, it is called as frontiers or yield of the tree. These are some of the syntaxes which are to be used inside this parse tree notation. So let us see how the strings that is to be derived with the help of these productions. So for example here, these derivations is called as sentential forms. That means to to get the result of the resultant string. For example, in this case, we are going to get the resultant string AAA and so what are the steps to be used for this one? So we have taken a first starting node, that is given one, S derives A small capital S B. So it is one of the production which is given in the list. So we are going to construct a tree based on this one, and to get the resultant. To get the resultant means to obtain this string, that is AAA, B. Then we have taken S as one more thing, that is A capital A S B. So once again we apply S. So in this way, the first time substitution of the production, getting some derivation, and second time substitution we are getting one more derivation, and then third time. So in this process, the final resultant string that is to be delivered. Before the resultant string delivered, what are the steps that is to be avoided? These are called as sentential forms. Before the string that is to be delivered, the previous these are called as subsystem or subtrees of the particular tree. So it is the main root ASP, and then remaining all subs. we are going to see that how this construction of this parse tree with this notation, that is A derives ASB, and then so this is the parse tree generation. For the given example, another example also we have taken a different example maybe here in this case. So here in this case, S derives capital S. Yes. So this one we are going to get S derives capital S. But in the next process of derivation, A capital S, B capital S. That means we are going to generate a subtree of the parse tree. Subtree of the parse tree, that is children. Children, or sometimes none of them are in the subtree also. This is called as partial derivation tree. Partial derivation tree is a subtree of parse tree such that either all children of the subtree or none of them in the subtree. So, for example, in this case, you have to consider the string that is derivation A capital S B S. So, what is the string that is to be applied here? The left, that is S to be A S B. And then the leftmost, that one, that is capital A, and then S derives epsilon. So, we are going to put this S derives epsilon. S derives epsilon. So, that remaining BS. Remaining BS. So, BS is. So, the next case we are going to apply the capital S with ASP. So, this is the derivation we applied. And then based on this, we are going to get next derivation capital S. So, capital S, once again we write ASP. And then we are getting this resultant string. So, ASP. So, from this we are going to write. So, here S derives epsilon. ABWA. The derivation tree, first derivation tree, which is different from second. That means here the first derivation tree is a subtree of the next most derivation. So that's why here we use the next S, which is to be derived with capital A and capital S B, and the same, that is next subtree that is to be generated here, capital A, small a, capital S B. But here the last string that is to be subtracted, these are called as subtrees of the remaining trees. In this derivations, we may apply either leftmost or rightmost also. We may apply either leftmost or rightmost also. Sometimes the derivation trees from moving from left to right, and then sometimes we are going to move from right to left. So it is basically a sequence of production rules in order to get the resultant input string. So previous also we have get the resultant input string by repeatedly applying several productions. So where we have to suitably supply it, that is to be most taken care. And we may have the various choices to replace particular non-terminal, which of them to be replaced. So I told that which of them is to be replaced. So to get that resultant one, we can replace based on our choice also. That choice is depends on the derivation. So that derivation may be two options. So the suitable non-terminal that is to be replaced either by a leftmost, then it is called as leftmost derivation. If that is to be substituted at the rightmost or right to left, then that is called as rightmost derivation. So which non-terminal is to be replaced? We are going, final result is getting the resultant string. So in order to get the resultant string, we may move from either replace, that is a non-terminal replacing either left to right each, then it is a leftmost derivation LMD, where right to left, it is a rightmost derivation. So there are two types of derivations. The derivation tree, that is, one is leftmost derivation and second one is rightmost derivation. So quickly we will see that how it is to be evaluated leftmost and right. So in this example, there is a production rules are given. So here in this production rules, first production rule is x derives x plus x, second one is x derives x star x, third one is x derives a. But the resultant one is, you have to string is given, that is a plus a star a. So according to the leftmost derivation, a left sentential form, that is means all the derivations that is to be substituted left to right only. Whereas in the case of rightmost derivations, all the non-terminal that is to be substituted with the right sentential forms only. So the substituted non-terminal, replacing non-terminal at the rightmost place. So first see that leftmost derivation in this one. So first we have considered the we can take any of the out of this list. You can take a privilege of taking any one of the production as per our the requirement. So we have taken one production x star x, but since it is a leftmost derivation, so we are going to take the leftmost non-terminal. So here leftmost non-terminal is x. Then that is to be replaced with the corresponding production. So what is the production that is to be replaced here in this case based on the resultant string? So here the string is a plus a star a. So that's why already a plus a star a resultant string. Then the string that is replaced x must contain a plus operation. So that's why you have taken x plus x. So star x is already available, that is same as this one. So that's why we have taken a new production which is available in the given list of production, that is x plus. You can also take x star x, but that may not give the result of the resultant string. So that's why we have taken x plus x. So in this, the leftmost non-terminal is x, that is to be evaluated with the x derives a. X derives a. Then leftmost non-terminal is x. Then that is to be resolved with the a, similar x derives a only. So we are getting one more thing. So next leftmost terminal is capital X. So we are going to replace with x derives a as non-terminal. So replacing of the non-terminal at the leftmost non-terminals, and then we reach to the right. Whereas if we come to the rightmost derivation, we have to come from the rightmost non-terminal that is to be replaced. So here our task is to reduce the resultant string a plus a star a. So a star star a that is x star x, and replacement of x is required. So that's why here we can take either option of either x plus x or x star x or a. So we have taken the procedure, that is the resultant one is x derives a. So the x derives a. Then the rightmost non-terminal is capital X. So in this rightmost non-terminal capital X, I may take the production rule x plus x. In order to get why you have taken x plus x, because the resultant derived string is a plus a star a. So to get the result of a plus a, the production or suitable production that is available, non-terminal replacement is x plus x only. So I cannot apply x star x. Why? Because already star is available. So I can take only x plus, option is only x plus x. Then we are going to derive x, rightmost non-terminal x derives a, then rightmost non-terminal x derives a. So the final result is a plus a star. So in this one also we are getting a plus a star a, but the result is same. That means a plus a star a for the leftmost derivation, and a plus a star a is the rightmost derivation, and this evaluation is done from left to right for one case, and the evaluation done from right to left. That means left sentential forms we applied and reached the resultant string, and in this case we applied right sentential forms and reached the resultant strings. So this x plus x star, this x star x, x star a, these are called as the sentential forms of the rightmost derivations. We can also build the tree corresponding wherever we get that one, that is called as parse tree notation. So it is very simple as that the applying of the production rules. So first initially we applied what is the production here in this one, x derives x star x. So the same thing here we are going to write these as a step manner, x derives x plus x as first production, and second production, that is here after apply the leftmost non-terminal is to be evaluated. So here leftmost is capital X, we are going to determine is x derives a, then x star x, we are going to write, then evaluate this non-terminal as x star x, then x capital A, and then rightmost non-terminal, that is leftmost x capital A, small a. So x derives a, we are getting x plus x, first x derives a. So that's why the step 2 is obtained by after substituting the production, x derives a. So that's why this portion is said to be the leftmost derivation evaluation. And then from this, the step 3 is generated with the help of this tree, this subtree. This subtree is x derives x plus x. Then after step 3 obtained, then leftmost non-terminal is evaluated, that is this one, that is x derives a, that is step 4. And step 5, which is to be obtained from step 4 by resolving this, that is x derives a, which is to be substituted, and then all the non-terminals from the leftmost to the rightmost are to be replaced, and the resultant string to be processed with the help of this Parser notation by knowing the each of these leftmost, that is each of the children. That is, for example, here x, that is in this branch we are getting a no, that is a, and then this plus, and then a for this branch a, and then for this branch star, and then finally this branch a. So the resultant string is a plus a star. So we are getting this, and then this leaf, and so in this way we are going to get the resultant Parser notation for the leftmost. Similarly, we applied for rightmost also. Rightmost derivation, here in this case x star x, it is leftmost and rightmost. So we applied this one as this. So this portion is derived as x derives a, and from this step 2 to step 3 we are getting this x plus x as the rightmost non-terminal, that is x derives x plus x. And from this, the step 4 is to be delivered with x derive rightmost x derives a. And then from this we are going to derive, that is step 5. Step 5, the rightmost non-terminal, that is x derives a. So all the non-terminals are to be evaluated, and then we are getting the result, that is same result as a plus a star. But remember that this time we applied these derivations from the rightmost. So here also we get the or child orders for this branch, we get a, and from this we plus, and from this branch we'll get a, and from this branch we'll get star, and from this we'll get. So the resultant is a plus, for this one a, and then for this star, and then for this subtree. So the resultant is a plus a star. So here keep in mind that rightmost, and rightmost non-terminal, and then from this step rightmost non-terminal, and from this rightmost non-terminal, that is to be replaced and substituted the corresponding sentential forms, the resultant string as a rightmost derivation to be applied. So once we get the sentential forms, it is easy to construct the Parser tree also based on the derivations which is applied, that we are going to get the result. So it may contains non-terminals and terminals, that is the body of this one. So sentence but contains only terminals, whereas sentential form contains both terminals and non-terminals also. A language grammar is generated written with L of G is a set of sentences. So what is the same? With the help of sentences only you can generate that particular language. So one of the production rules is given as an example. Here in this example, E derives E plus E derives E star E derives ID. So the string to be determined is ID plus ID. So we applied the leftmost derivation as well as the rightmost derivation. Here leftmost derivation, the leftmost non-terminal, that is to be evaluated with the help of this E, and then that is to be replaced with the corresponding strings to be substituted is here E plus E. Why? Because the input string is ID plus ID star ID. So that is replaced with E plus E, and then the corresponding ID, E derives ID in this case, and then E star E, leftmost one is capital E, once again ID, and then leftmost ID. Similarly, rightmost derivation, we can apply either E plus E or E star E. So we applied E star E, and then in this, the capital E determines ID, and nextmost non-terminal rightmost here capital ID, E derives ID, and then from this, so we are getting all the replacement with the corresponding substitution with the non-terminals capital E leftmost, rightmost non-terminal, rightmost next non-terminal, rightmost next non-terminal non-terminals. So here nextmost non-terminal after generating E plus E star. So in this way we are going to generate derivation trees, and then we are also easily construct a parse tree also. You can easily construct the parse tree also for this examples. So all the contents and this diagrams and production rules chart to be available taken from this book, that is Compilers, Principles, Techniques and Tools by Sati Woolman. So you can find the contents. And our next class will come up with a new topic, um, and today we are going to stop this session. Thank you very much, all of you. Thank you once again.
Like, share and subscribe. Hit the bell icon for more updates.